Hey everyone, I'm Natalie Cohn, your community manager for Scale's AI Exchange community. Happy Thursday! It's a pleasure to have you all tuned in today or this evening, depending on where you are in the world, for our event, Open Climate Fix, ML Solutions to Global Climate and Energy Supply Crisis, with Jacob Bieker and Canute Haroldson. I'll introduce our speakers in a moment, but first I wanted to make an announcement and give you a little bit of support navigating the community platform. After the presentation today, we will host a live Q&A with Jacob and Canute. If you have completed your member profile, you can join us there and get FaceTime with our speakers. In order to make your way to that intimate Q&A, look to the left of your screen for the Agenda tab. Select the Agenda tab, and then you'll see the live Q&A option as a segment of the agenda. When you select Join, you can meet up in a roundtable room where you'll mute yourself and drop a line in the chat if you have a question or comment, and I'll call on folks in the order I see them in the chat. Alternatively, you can join the live Q&A by selecting the notification Join Now pop-up at the top of your screen toward the end of the presentation. Next week, I'll be hosting Mehul Smitry Rajay, former Ground Truth ML engineer at Neuro, and a Grace Hopper Abbey Award winner for her advocacy in creating access for young women engineers in an AI exchange event. Janie, our community coordinator, is dropping a link in the chat right now for that event. And if you missed it, last week I also published one of our most popular recent events, OpenAI's Instruct GPT with Long Wu Yang and Aaron Kim in article form. Similarly, if you missed the first event in our Metaverse series, Microsoft and Mixed Reality, Revolutionizing the Productivity of the Front Line, that recording is now published on demand. So on to our guest speakers for the day. Jacob Bieker is a machine learning engineer at Open Climate Fix and formerly a machine learning research engineer at Scale AI. Jacob received BA in physics and computer science from the University of Oregon and dual MA in astronomy and data science and astrophysics from Leiden University. He has extensive experience oscillating from research ideas and raw data to implementation and results, especially as related to machine learning methods. His research interests include computational astrophysics and biology, observational astronomy, supercomputing visualizations, high-energy physics, natural language processing, and other interdisciplinary research areas. Jacob Bieker's research experience is rooted in collecting massive sets of data and analyzing those sets to produce insights. Canute Haroldson is a delivery manager at Scale AI with a lifelong passion for reducing waste through automation. Before joining the operations team at Scale, he worked in the solar industry, first developing novel commercial design techniques at Sun Edison, then driving customer success and education for solar software company Folsom Labs. Canute holds a dual BS in mechanical engineering and public policy from Carnegie Mellon University and is currently working on an MS in sustainability management at Columbia University School of Professional Studies. Now let's welcome Jacob and Canute to the stage. Hello, fellas.
Hello.
Hi.
So good to have you.
Great to be here.
Yeah.
Jacob, I found you because you were formerly an ML research engineer at Scale, and we're so honored and happy, delighted that you decided to join us for this event today as you've moved on to saving the world.
Well, I'm glad to be back.
And Canute, this is really special for us too, because we used to work in operations together, and you were even one of the very first interviewers that interviewed me, and so really played a significant role in me being here working with Scale. So it's really nice to be collaborating with you in this capacity now.
Yeah, great to join, and also great to be able to talk about solar a bit more again.
Awesome. Well, without further ado, I'm going to leave the stage and leave it up to you guys, and I'll join you a little bit later so that we can source some questions from the audience. And I will also give the audience a little more instruction on how to join the live Q&A when you guys are finished with your presentation. All right, bye, fellas.
Cool. Okay. Yeah, so I'm talked about state-of-the-art ML-driven solar generation, PV generation forecasts. Quick background on what Open Climate Fix is. We're a nonprofit company, now 7 people as of this week. with a lot of experience in both energy at the UK's national electricity grid operator, Habitat Energy, Siemens, and like PhDs in energy disaggregation, but also machine learning with experience at DeepMind, NASA, and also Habitat. We have a lot of funding from, our main thing is with the UK's national grid, where we are trying to forecast their national PV generation for the next, up to the next 48 hours. But we also have funding from Google's Impact Challenge, where we are going to take this PV forecasting to the rest of Europe, and recently got some funding from the UK Research Innovation for forecasting individual sites like solar farms and like household solar as well. So there's a problem in the energy industry where the industry is quite risk adverse, and taking state-of-the-art research and making it something operational can be a mountain of pain and quite difficult, especially for an industry that doesn't necessarily have a lot of ML experience. And so we at Open Climate Fix try to bridge that gap. So we take current state-of-the-art models, re-implement them, or take their open source implementations and build on them into an operational forecast, and then also provide this forecast to an energy industry, so that like National Grid and other grid operators can just take an API request of how much solar is being generated and don't have to deal with all the complexities of large transformer models or other things like that. Can you switch video? So this is essentially a video of what we're trying to do at Open Climate Fix. We are trying to do nowcasting, which is essentially just another name for very short-term forecasting. So this is a video of the UK with a couple, roughly I think 2,000 individual PV sites scattered around that we have live data from. And the darker they are, the darker blue, the less generation they have. If they're orange or yellow, then they are generating at their max capacity. And the actual video is the live feed from a geostationary satellite from EUMETSAT, which is every 5 minutes, covering all of Europe and North Africa. So we're trying to forecast essentially where the clouds are going to be, because for solar, that's the biggest change in how much generation you're going to have. And forecasting clouds is somewhat difficult. They kind of pop out of nowhere when they form. They can move quite quickly. Numerical weather models are quite bad at predicting where clouds exactly are going to be. So what we're trying to do is combine multiple different data sources to have very accurate short-term forecasts. And these clouds can cause very quick and very large changes in the total amount of energy being generated for the UK or for any different region. Can I switch back to the slides? These better solar electricity forecasts both reduce costs for the grid, and what we most care about at Open Climate Fix is reduce carbon emissions. So one of the biggest things with solar is that it's one of the largest sources of uncertainty for the UK's national grid. And this uncertainty manifests itself in requiring a lot of backup power in case their forecasts are wrong. So this backup power is called spinning reserve. It's essentially giant jet turbines on the ground that are just idling most of the time. And if the national grid's solar forecasts are wrong, they have to ramp up these generators really quickly to replace the power that they thought they were going to have. The downside is they're quite inefficient when they're not running at full capacity. So they emit a lot of CO2 emissions and are very expensive. Roughly 2% of every UK electricity provider's bill is for these so-called balancing costs. So yeah, what are we doing? We are building both advanced ML things, but also putting in production and trying to make it very easy to use for non-ML experts. So this is an example of our UI. You can also get from API, where the UK is divided into around 317 different regions. And we forecast for each of those regions individually where how much solar there's going to be over the next, in this case for this model is 8 hours. As you can kind of see, because you kind of see where clouds are going across the UK at this point, where it's not as yellow is where clouds are, or clouds are forecasted to be. And brighter yellow is where it'd be more clear days. This is in the amount of capacity. So this is the same forecast, different time period, but still at around like 1 o'clock when it's a maximum in the UK. And you can see in terms of like the total amount of power in the UK, most of it's in the south. Scotland doesn't have a lot of solar power. It's not very sunny, but the south has a lot. And so if there's clouds over the south of England, that has a much bigger effect on the total amount of solar that we have. So how are we doing it? There's essentially two different main ways to get these solar forecasts. The majority of companies try to do physical models. So like use giant weather forecasts from like NOAA and the Global Forecast System, or we use the Met Office's UK forecast. This essentially divides the world and atmosphere into giant 3D voxels that use known equations of the atmosphere and physics to go into the future, usually days or weeks and sometimes months. They take a very long time to execute. They are run on huge supercomputers. Forecasts are usually delayed 1 hour to 3 hours from their initialization time. So we don't have the most up-to-date information from these models. And they're not particularly designed to forecast solar irradiance and solar power. They're more built for like tropical cyclones and like waves. For affecting what affects like transportation and other parts, other things reliant on that. On the other hand, AI and ML have proven to be very good at a lot of different problems recently. If you have a lot of data, we can assimilate more types of data. So like live satellite readings and live readings from panels on the ground, and it's very fast to execute. So for example, we create new forecasts every 5 minutes. And we do that for all 317 different regions. Our models are very quick on inference and pull in quite a lot of data. So it works very well for our short-term forecasting needs. How we approach it is all of our models take a lot of different inputs. So the most important one is the actual readings from like systems on the ground. So either readings from like individual panels that people have hooked up to a website such as pvoutput.org, or there's some readings that the National Grid has that we can pull from and feed into our models to help make sure it can take the recent history into account when doing these forecasts. But then you also have the actual numerical weather predictions, especially for like long-term forecasts, so more than the next like 12 hours. Numerical weather predictions are quite important. And then you also have satellite imagery for quite fine-grained and very recent like locations of clouds, essentially. We have geostationary satellites that take images every 5 minutes, and we can have a high resolution, very frequently updated location and movement of where the clouds are moving, so we can forecast them into the future. Additionally, we have topographic data, so like elevation data, which has effects of, especially with clouds, like if you have a mountain range, clouds will probably be deflected at some point, somewhat by that mountain range, or if it's flat, it might move quicker. So topographic data is quite important. All of this goes into our different models, and we can then forecast like national PV or regional or individual sites, depending on what we want to train a model to do.
So Jacob, one thing I think that's really interesting there is that, you know, especially for topography, but for those people who have been in solar, the idea of dew point temperature is another really important value. So that's, you know, temperature, but including pressure and humidity into that valuation. Those end up having a huge effect on solar performance. And certainly in the UK, something like dew point is much more of a worrying thing given the level of humidity. But those are also really difficult to predict. So in terms of incorporating what feels like that very minute data, that very localized data, maybe this is something we'll get to talk to, but how do those end up being pulled into an ML model that ends up being so pulled back given the geostationary satellite data?
Yeah, so that's where the numerical weather predictions come into effect. So they have predictions for a lot of these different variables, like the temperature and humidity and things like that. And so we can use those. We know it's not very good at forecasting irradiance directly, but they are quite good, especially for like other physical variables. There's been a lot of work to make sure that they're pretty good at forecasting temperature and forecasting other parts of the atmosphere. And so that's where that physical knowledge comes in. And we try to helps ground it with the actual physics part of it. That data should also be somewhat incorporated into the actual readings from the PV panels. So if the dew temperature is affecting how much they're generating, that should show up in the recent history. That will probably stay the same for at least the next couple of hours. So that, the model should learn based off of that.
Awesome.
So here's a few different ways that we've been working for that model part of it. So there's been quite a few models from Google Research and DeepMind on forecasting precipitation, and precipitation comes from clouds. So our thought was that we could then take these models and help them convert them to work for forecasting solar directly. One of them was called the Deep Generative Model of Radar. It was done by Google DeepMind and was built to forecast the next hour and a half of precipitation in the UK and US. It worked pretty well. It was again to make probabilistic outputs. Probabilistic outputs are quite important for like the grid operators, because they want to know what's the probability that we're wrong by a very large amount, or are we pretty certain around the mean value that we're forecasting. And so for this one, we created an open source implementation and modified it to be able to take in more multi-channel images and more other data sets so that we could predict. Originally, we were thinking we could predict future satellite imagery with this, and then go from that to another model to predict the actual PV. We're still working on it with it a bit. But this is one of the ones we're trying. Another one from Google Research was Netnet, or Netnet 2, where it's another weather precipitation forecasting model that takes in essentially a very large context area and then your area of interest. So it can capture like the clouds that are far away but might cross into your area of interest within your forecasting time horizon. And also outputs, again, probabilistic outputs. So we took this, we took this small architecture as well. We implemented it again in PyTorch and publicly, and are now using it or researching into it and running it right now for our national 48-hour forecaster. And it's quite nice. It takes, in the papers, it takes a lot of the same modalities of data that we're using. And so it seemed like it was a pretty good fit. Our baseline model was a simple convolutional 3D model we call PVNet. It just has two branches, one that takes satellite imagery of the last hour, and then it takes numerical weather data of the last hour and the next 8 hours, and runs it through two different branches, and then combines them at the end with some historical PV data. This model is actually works quite well. It's a pretty good baseline, and it's very simple and easy to train, which has nice advantages of it. But this is our current baseline that we still use. And then we have been seeing some other research from DeepMind, such as Perceiver.io, which can take in multiple different modalities and then does the cross attention and self attention on like a latent representation before giving multiple different outputs. And so we built we were called Optiflow, because it combines optical flow, the satellite imagery into the future, with the Perceiver.io architecture to forecast a mixture of Gaussians for how much for the regional PV generation for the UK. So take in, a different region and then try to output what's the probability that it will, for the future forecast. For our results, we have a baseline of the National Grid's current UK forecasting, which is better than persistence and does okay, but has pretty high error overall. So nearly 10% regionally and just over 8%, 9% nationally. The PVNet is the simple convolutional 3D model, and it does quite well nationally and quite a bit better so regionally. And then our power perceiver model is a small extension to the Optiflow, or similar to the Optiflow kind of model, but using some other open source contributions and a few model tweaks. But it's currently our best performing research model. It's over 3 times better than the National Grid's forecast over the next 2 hours. And so this seems to be a good point for AI and ML models doing much better than the current ways of forecasting.
Yeah. And I think one of the really interesting things there is that the idea of predictive views of the weather is not particularly new to solar. I mean, that's kind of the whole piece of this talk, is that we are comparing prediction. But when we're actually looking at the difference between the National Grid's prediction and what OCF is giving out, we can see just how much lower that actual error rate is. So especially compared to traditional models of irradiance modeling, so TMY data, things that take a typical span of time and say typically this is what we're going to see. What is that the point where you see the main difference between what those typical predictive models are and what Open Climate Fix is developing?
Essentially, those typical models. Obviously, if you're going with typical, you're not going to include any actual cloud movement and things like that, which can cause very large, very quick changes, which is actually the thing National Grid's most worried about. For example, in the UK, if a big cloud goes over Cornwall, you can lose something like a gigawatt of power or 2 gigawatts of power, which, considering the entire installed capacity in the UK is at most 14 gigawatts, is a seventh of it, which is quite a lot, and very, very quickly, within 5 minutes. So I think a lot of our errors is we can forecast as very short, quick changes that those kind of models, more typical models, will not be able to. And just, having more recent live updated data, it makes sense. It should give you better short-term forecasts. On the longer term, I would expect the performance of our models to effectively regress to the mean of those typical models, because if you're forecasting months in advance, you're not going to, clouds today aren't going to affect it 5 months down the road. So
but it is an important point of differentiation there, that yes, against the mean over a long period of time, not necessarily going to be a difference, but that's not actually the problem that we're solving for here. So, which I note for the energy wonks in the room who are probably thinking about that. And I think another interesting point there that you've mentioned earlier, but is worth reiterating, is what is the actual time frame for that prediction? So for people who are particularly concerned with the deployment of other resources, with how much this error rate is going to affect if they're spinning up different reserves, they're taking up, starting up new types of power to actually meet the demand or the potential error rate. Do you see that actually affecting the time to spin up those reserves, to even avoid having to spin them up altogether? And how far in advance is that actually partnering with something like the National Grid with these really short-term predictions for, hey, in 5 minutes, Cornwall's going offline?
Yes. So most power generators, like coal plants or most natural gas plants, take quite a while, like a few hours to come up. And so you can't, if there's a short-term change, you can't start them from cold and have them generating enough power. For that's what those gas turbines are for. They're the ones that can react like within a few minutes or half an hour and ramp up and replace like very short-term problems, like turning off or not turning on coal or gas plants for tomorrow is what we're now extending our forecast to for 48-hour things. So yeah, there's like a few different ways, a few different forecasting teams at National Grid that do on different settlement periods. So one's like the next 4 hours, 4 to 8 hours, which is what our current one is now doing. The PVNet is doing operationally, which would be, oh, let's not ramp up that gas turbine, or let's maybe shut some of them down for now because the next few hours we don't need it. And then the Netnet based models, or potentially other ones, depending if they do better, for the 48-hour forecast would be like, oh, maybe we don't need to turn on this gas plant tomorrow because we are very confident that we'll have enough solar. So yeah, they kind of work on slightly different scales, but that's where the very short-term forecasting matters for that. And then we can go into a little bit of where we actually get the scale in our forecasts. So we've done some ablation studies, and this is on PVNet. This is for the inference scale, which makes sense. The most dominant part of it is the actual history of the live systems. So if you have like the live systems up to 5 minutes ago, you can do a pretty good forecast into the future on its own, just off of that. Another one is a few percentage from solar geometry, which is the like elevation and azimuth of the sun compared to that panel's location. And then you still get another 40% from different, or like 43% from different like Earth observations, either the numerical weather models or the satellite observations. So the weather forecasts, this is for up to 8 hours ahead, do a pretty good chunk, roughly a third of the total scale, because they have a lot of the physics is baked in. They're tested by millions of users, and they have, I mean, the whole Met Office is building these kind of models. They do a really good job of a lot of the other physical attributes, even if the radiance isn't always the best. And then the satellite imagery helps provide another 40% from that Earth observation, or 60% of the total, where we get where we can essentially help correct for the issues of like cloud forecasts from the weather forecasts with like the actual imagery that we see in the satellite imagery.
Yeah, and I think one of the really interesting things here is, one, it's important to not downplay just how much this satellite imagery and the considerations we're making off of that affect the actual accuracy driver. But one of the really interesting things historically with the solar industry is that 51% PV history side of things. And I think a lot of solar owner and operators, particularly the larger ones, the ones who have a larger like grid distribution capabilities, say, oh, to some degree, that's our bread and butter. That's our secret sauce. That is the thing that puts us above other operators, not necessarily their operations, but their understanding of what their operations are and that irradiance data. So how does OCF balance that fact that you want to have perhaps this access to this sort of data? You want to have predictions given the fact that historically these solar owners operators have held onto production data as their proprietary information.
Our main way is essentially we ask nicely. It is somewhat difficult to get. This data is quite sensitive for a lot of these companies. Part of our argument for having them share it with us is that for these solar farm operators and things like that, if you can better forecast your power generation, you can generally, at least in the UK, sell it for more, or you'd be more confident when you're selling power to the national grid. And so you can make more money off of it. So there can be a financial incentive. currently, most of our PV history is from either National Grid collects some data, which for like very large solar farms, they have to be metered, and the National Grid just gets that data so they can pass it on to us. But also the website pvoutput.org, which is just people that are technically inclined hook up their panels. And we use that to get live readings, which can be quite noisy. The data isn't very clean. The metadata might be wrong. It might randomly drop out, or maybe some of the metadata is just wrong, like how much power it should be able to generate and things like that. But it still provides very useful historical information. Yeah, mostly asking nicely currently.
Yeah, and is that then something additional that Open Climate Fix is looking into? Is you have this messy metadata from smaller operators. I think, traditionally the view within the industry has been, oh, you're only going to get enough useful information from utility scale installation. But are you getting enough from that metadata in aggregate, or do you have future plans to better compile that data to be a guiding kind of a guiding direction in irradiance generation and PV history?
Our primary thing is, we try to figure out and essentially correct for the metadata by like looking through the actual generation data over the last however long we have from these different systems. So certain ones like we know are now faulty, and so we take them out of our production set or training set. Other ones we can somewhat infer some of the metadata. We can generally tell, or we're working on trying to figure out how to tell when the metadata is wrong quite robustly, but currently it's more of a step like individual example period. But like one example is there's a huge amount of panels that are put in at an angle of 180 degrees that doesn't match the rest of the distribution, which we're pretty sure is just because people installing them are like, it's close enough. So there is issues like that like are known, somewhat hard to fix, but we should be able to tell if we have a couple years of data of how actually angled it is based off how the capacity should be. It's a bit difficult. We do get some data from like a company which is a lot more standardized and they have more control over it. So we like that data quite a lot for like the higher quality, but we found our models, just like with most ML things, the more the merrier, and they work better when we give more history.
Fair enough.
Yeah. And then I'll get a bit more into how OCF works. And part of this is we want to maximize our impact. So as part of quite a few different projects, we've tried to estimate how much actual carbon savings we'll have based off these improved solar forecasts. The best estimate we could come up with, which has lots of caveats and assumptions into it, because it's quite hard to actually tell if a better solar forecast directly reduces CO2 or not, because everything in the grid goes through people, is that we could save around 100,000 tons of CO2 a year in the UK by improving the forecast by 50%. Roughly 1 million tons of CO2 a year in Europe and 100 million tons globally. So could be quite impactful. We also know we're quite a small team and we don't have the expertise necessary to do it for the whole world ourselves. So we try to leverage open source and making everything public, hence the Open Climate Fix. And now there'll be a lot of opens on these slides. Our idea of having open data, open models, and open research. So all of our training data, as much as publicly available, is available on Hugging Face and Google public data sets. A few things like the Met Office's weather forecasts we can't redistribute, but we have all the code there for other people to collect it with like API keys. All our training codes and model weights are also released publicly. Our production pipeline and like Terraform code and every part of our stack is public and accessible. Nearly everything that we make in Python, which is most of our stuff, we try to make pip installable and designed to be easily extended and work as like a library for other energy forecasting needs. And all our development is in the open, with all our research ideas and results public on GitHub and GitHub issues and chats and stuff in real time as we do it. Because we want to have, essentially throw everything out there and see if anyone else can make it better or can use it to make something really cool. On the open data side, we've processed like dozens of terabytes of weather data from very somewhat archaic and hard to use formats to more normal geospatial formats such as ZAR. We've released, we think, possibly the first PV, like multi-year PV data set of like actual live readings, at least of the UK, of around 25,000 different systems, covering currently, I think, 2 or 3 years, and we have plans to extend it more. We've released 8 years of European satellite imagery, 5-minute satellite imagery, like in the videos that were shown, in both that high resolution channel and 11 other channels. As part of this, we've also released multiple years of US, Swedish, and UK precipitation radar data and all the code to easily collect and collate more. We plan to hopefully automate this even more so it can just continuously release more and more data publicly. We also have a lot of open models. We have dozens of different pre-trained solar forecasting models on different input modalities and architectures. We've re-implemented a lot of different papers from state-of-the-art papers, like the DeepMind and Google Research ones that are talked about, in addition to our own models. We've also tried to collate and release matching or similar data sets to the papers if those data sets weren't already made public. So, for example, the Netnet data set wasn't released, but we've been trying to recreate it for the US, and we have all the data public for a somewhat similar data set over the UK or Europe. And create our training flexible training pipelines in PyTorch's new data pipes so that people can work with all this data without having to build everything themselves. And then, probably the most important for us is the open research part of it. So all our research progresses in the open. We've helped run some hackathons. Climate Hack AI was the biggest one, which was 25 of the world's top universities, where we help give them the data and help devise them. So they're trying to forecast future satellite imagery. And we end up using the Winnings model in our power perceiver model, or a slightly modified variation of it. Idea is that anyone can participate, from like 16-year-olds to PhD students to industry researchers to anyone who's curious and wants to log into GitHub. We've also co-supervised multiple bachelor's, master's, and PhD projects from people at Stanford, UCL, Edinburgh, Queen Mary University, and various other ones. And our for the open research, our current research we're working on is both more like direct PV generation models, trying graph neural networks and potentially diffusion models for like trying to create large ensembles of weather forecasts quite quickly instead of relying on the big supercomputers for everything. And pseudo-labeling PV data. So instead of those like points you saw in the video, we could instead try to label every single pixel in that image and do pre-training our models on that. So we have like 1 million-fold more training examples. On our more ML models, part of it is trying to combine different other state-of-the-art models. So like hierarchical perceiver from DeepMind and Netnet version 2 to forecast national or regional PV in a more unified model and potentially more advanced than our current ones. Also, there's this paper by Ryan Kiesler earlier this year that used a graph neural network and did pretty good forecasts of the global weather systems, being able to replicate the current forecasting systems on a single GPU and make like 1,000 ensembles in a few seconds. So versus the 50 or so that the big weather forecasters make. It's quite flexible. So we're trying it for forecasting future weather quite quickly, and along with potentially directly PV or any other thing that we're curious about, or directly assimilating the raw weather observations and skipping one of the steps in the weather forecasts that take about usually an hour or two to run, to try to speed up the speed that we can get new forecasts. And another one that we're going to start working on is pseudo labeling PV data. There was a paper from OpenAI that trained a really good Minecraft model based off of essentially having it pseudo label a lot of YouTube videos by taking both future and past frames and then labeling the one in the middle. So essentially having it cheat to give better labels to then train another model on. And we think that could essentially, that same kind of idea could work quite well for this PV data and give us, a huge amount of synthetic training data to use on our models. So then the end results is we want to have easy use forecasts that update in real time with lots of engaged users. And hopefully the open approach guarantees a lot of continuous improvement because we can build on as many people's ideas as we can, and other people can take our stuff, make it better, and hopefully have the biggest impact on climate that we can all do together. So thanks.
Awesome. And then I'll just throw in one more question before we go to the audience questions, because I've seen a lot of really good ones coming through. But I think the last piece that's kind of a more meta question to these last slides is, what does Open Climate Fix consider as the role of industry in providing these resources versus the role of government? One of the big things about these past predictive resources in something like the US is we had TMY data sets extending up through the mid 2000s, but then suddenly lost access to these as there weren't groups going and actually collecting this information. There's been, some design around stuff like the NASA PVM data, but again, that's satellite based and doesn't provide as much of that on the ground information. So for a group like Open Climate Fix, how do you view that role of maybe what Open Climate Fix is either providing or enabling for that government stance on energy deployment?
Yeah, I think there's definitely roles for both. So one example is in the UK, up until a few years ago, if you installed residential PV systems, you could get, it's called a feed-in tariff, you could get paid for your solar panels. But as part of that, you had to register metadata about it and where it was. And once that program stopped, people stopped doing that. So there's roughly an estimate of between 5 and 10% of all PV installations in the UK. We don't know where they are, which obviously makes it a bit hard to forecast them if you don't know where they are. Let alone we don't know at all the capacity or how much power they actually generate. So having that government support or schemes or requirements for installing installers to report things to a central body, which seems ideal for a government to do. Industry, it's I think maybe with some pushing from governments, but trying to be more open on data. If the more data, for example, that we have, the better solar forecasts we can make. Theoretically, the more money they can make. So there should be a more aligned system, but a lot of solar operators are quite secretive. We are getting some more partnerships now with some recent innovation funding for working with individual site level ones, but it definitely is more of a kind of negotiation, takes a lot longer than we would ideally hope for.
Yeah, that's fair. But I think, worth calling back to that slide is saying, think about this additional 40% in accuracy calculation for any solar operators who happen to be on the call, who happen to be watching the recording, for utility operators. I think that represents just how significant of an impact there actually is to being willing to share that data. And, for your ability to negotiate some of these contracts further in advance in terms of deployment, all things told, when you consider the industry and how that money ends up getting made, it seems pretty much the best sort of win-win scenario that you could come up with.
Yeah, and that's what we hope will start to convince more people as time goes on, especially as we get maybe some more users, solar farm users, and then maybe we can write about, hey, they are making more money. It's not just theoretical. Give us some of your stuff and we can hopefully make even more money too. The world slightly less carbony. So
yeah. Awesome. Well, I think with that, again, I didn't want to delay the audience questions too much, so I'll bring our I'll bring Natalie Cohn, our community manager, back in, and we can get to the stage to get into some of those questions, I think.
Yeah.
Oh, I think you're still muted, Natalie.
Hi, fellas. That was really wonderful. Thank you so much for sharing that presentation, Jacob. And I feel so lucky that we had someone on our team like Canute who has such depth of experience in this area. That was really insightful. And one thing before we go on to the questions, Jacob, I just want to say thank you so much for doing this work. I really admire how Open Climate Fix's work is all open source, and also how you guys are so dedicated to mentoring young research engineers so that we can expand solutions in this area. It's super important. And as a mom of a 12-year-old, obviously, I would like for these solutions to work. Okay, so the audience is curious if there will be a recording available afterwards. That's definitely something that I can answer. Yes, guys, there will be a recording. We typically upload all of these recordings on demand 48 hours after the event. So I will be editing this video right away, and I will make that available to you in the wake of this event today. Then Jenry Hernandez asks, you showed 4 different input sources. Have you made any ablation studies to which of these sources are more useful for the model?
Yes, I think that might have been before the slide on the ablation study where I was talking about the different inputs. But yes, we are planning to do a lot more with some of our more advanced models because that was on our most simple one. But we think in general it holds. PV history is by far the most important, and then satellite's quite important for the short-term bit.
Thanks, Jacob. Rafi Jane asks, is there a top-line estimate of how much energy is saved by the reduced error by the better models?
So it's, yes. So on that slide, I think it has it too, but it's, so the national grid's error tends to be around, or average error is around like 600 megawatts, 700 megawatts. Our best model is around 200 or 190 megawatts. So that's nearly half a gigawatt less error, which is quite a lot of energy that we don't need to then generate with fossil fuels.
Okay, thanks, Jacob. Amanala Chawachi asks, since FF reserves will always be needed due to inconsistent solar power generation, do these forecasts have a chance at reducing this need to zero realistically?
I mean, I think there's a few different ways you could do it. Not with how the current grid is. Part of the issue also with renewables, with their variability, is that the grids can't necessarily handle too much solar or wind. So like certain places, they're starting to like stop solar farms and stuff from hooking up to the grid because the grid can't handle it. And part of that is because they can't make good enough forecasts. So our forecasts could help then enable more solar. We're also planning on eventually doing wind and EVs, possibly in batteries and kind of everything in the energy system, but currently just focus on solar to enable more solar power to be installed and connected. So it should still reduce the need for fossil fuels. Also, if grids are more interconnected, there was a recent one where they created a virtual power plant between, I think, wind and solar in Spain and Germany. And they were able to essentially operate it like a gas powered plant. So they could move the energy around that they needed, and it kind of reduced the variability quite a lot. So research like that could also help deal with it.
Awesome.
Yeah, I think just another really important point there too is like thinking about what those reserves are actually coming from. You know, it's there is the need of some of these capacities to spin up quickly, but you know, if you look at more battery and storage deployment as a potential future, the idea that those sources end up being, you know, continually fossil fuels being versus being something that is enabled by that overproduction and goes into a storage system is important to consider. Of like, you know, here we're decreasing error rate, and I think like the application ends up being very much about how that affects the generation and utilization of things. But you know, in terms of reducing to zero, that's then also a question about how grids themselves, how countries want to shift away from fossil fuels being their spinning reserve deployment.
Awesome. Thank you, Canute. So Ravi Jain asks, what's the type of data that's provided in the PV history? Is it PV capacity, reliability, delivery, etc.? Is it per site?
So we have two different types of PV history that we get. So we have, there's a thing from the University of Sheffield called Sheffield Solar, which creates estimates for all of those 300 and something regions in the UK, how much aggregate solar is being generated every half hour. So we use that as one input for a lot of our things. The actual, for the individual sites, a lot of them, like all the dots in that video, were individual PV sites. It slightly varies. So for some of them, it'd be the amount of power they generated over the last 5 minutes. Other ones, it's how much power they're generating at the moment that 5 minute ends, so instantaneous power. They don't always tell us which is which, so it's another problem where we're not exactly sure. They don't tend to have things about reliability. We more figure that out from suddenly the thing. Well, the easiest one is, is a solar panel generating power at night, for example. Then we know something's wrong with what it's reporting to us. But it's more the metadata tends to be like the orientation and tilt of the panels, well, I think mostly that, the type of panel possibly, and the total capacity.
Thanks, Jacob. Jenny Hernandez asks, is this influence percent for those sources equal no matter the horizon? Or have you noticed that, for example, maybe satellite imagery has a larger influence percent for shorter horizons, but smaller for longer horizon?
So we're still doing the ablation studies on that now for our 48-hour forecasting model. So in the Netnet 2 paper that we're basing one of our stuff off, they kind of did this. So they were looking at even the individual bands in the satellite imagery. It seemed to mostly drop off by 12 hours of forecasting. Then the satellite imagery stops being super useful. So we would expect it to be most important at the very beginning and then slowly drop off over time as it gets more outdated and more clouds form that it can't see.
Okay, last but not least, 100 MT CO2e globally potentially saved by better forecasts. Did I hear that right?
Yeah, per year. So these are our best estimates. There's lots of caveats to it in terms of it was validated by some third parties as well when we came up with this, but it's very difficult to actually directly say how much is saved. So there's a lot of caveats. But our best estimate is globally the 100 million tons of CO2 equivalent per year that's saved by twice as good. I think it was twice as good solar forecasts.
That's a really exciting estimate.
Yeah.
Okay, awesome.
Clear, right? So.
Well, now we can give the audience an opportunity to meet you two face-to-face for a live Q&A. So just a little recap on instructions there, guys, is you will probably see a notification at the top of the screen. It's asking you to join the live Q&A. You can join us there by just drilling into that notification. Or if you don't see the notification, you can go to the agenda and then you can join now in the live Q&A section of the agenda. So I will meet you there. So will Canute and Jacob. And I hope you guys enjoyed the presentation. We'll meet you here next week on the 15th of December with Mehul. Bye, guys. Hope you enjoyed that.